high ampere, the radius of the conductor is R and is placed in the air, and it's a solid conductor, round, cross-sectional area is circular, and it's a long one, very, very long, like infinitely long enough conductor. The reason why we are assuming an infinitely long conductor is that we have to want to make sure that it complies with all the requirements to derive the formula for flux, and hence the inductance value of the conductor due to that current. So we are assuming that we have one conductor which is a solid round conductor having very long length, and its radius is r, small r, and carrying a current of I ampere. Now, because of this current I ampere flowing through the conductor, what will happen? A current flowing through the conductor of I ampere will cause some flux linking with the conductor. It will cause some flux linking with the conductor, and these fluxes that will be linking with the conductor will have two parts or two categories or two different names. First one is the internal flux, and the second one is called the external flux. So because of the current I ampere flowing through the conductor, there will be flux linking with the conductor, and those flux linking will come in two categories, the internal flux and external flux. That's the first thing that we have to remember. And now, how this internal flux and how this external flux. Now, the internal flux is present inside the conductor. The internal flux is present inside the conductor due to the flow of current of I ampere. And this flux actually does not link with the whole of the current in the conductor, but only a fraction, meaning if we are considering that a conductor is carrying a current of I ampere, that I ampere current is going to cause the flux linking, and of that flux linking there will be some internal flux, there will be some external flux, and this internal flux does not link with the whole of the current in the conductor, but only a fraction of it. So only a small fraction of the current is linking with the internal flux. And why is it so? I'll come to that later on. But for now, we need to remember that this is what we have so far. We have internal flux, we have external flux due to the current of I ampere, and the internal flux is linking with only a part of the current I, not the whole of I. Right, now we go to the external flux. Now the external flux is produced around the conductor. External flux is around the conductor, outside the conductor. And this external flux outside the conductor or around the conductor is due to its own current, meaning the current I ampere that is flowing through it, and also current that are flowing through the other conductors which are nearby to this conductor that we are considering. So this flux, external flux, is actually outside the conductor cross-sectional area, and it links with the entire cross-section. So this external flux is produced around or outside the conductor due to its own current of I ampere, and also the currents that are flowing through the other conductors that are nearby to this conductor that we are considering. This external flux is outside the conductor, internal flux is inside the conductor, internal flux is inside the conductor, outside fluxes causing external flux due to its own current and the currents in the other conductor. Now, when we talk about the inductance, it is related to the flux linkage. So when we have internal flux linkage, it gives us internal inductance. When we have external flux linkage, it gives us external inductance. So the inductance itself is related to the flux linkage of a conductor. So the flux linkage comes from the internal flux. Flux linkage comes from external flux. So that is why we are going to get internal inductance and external inductance. So internal inductance can be denoted by L, capital L, IN suffix, and then the external inductance can be L external EX. But the total of these two will give us the inductance of a conductor. So that's why we will add those two inductances, internal and external inductances, to get the total inductance of a conductor per unit length. We need to again remember that it's in per unit length inductance per meter. So total inductance will come from internal inductance and external inductance. Internal inductance is caused by the internal flux linkage. External inductance is caused by external flux linkage. Internal flux linkage is within the conductor. External flux linkage is outside the conductor. Internal flux linkage is only due to a portion of the current that it is carrying. External flux linkage is due to the current that it is carrying plus the currents in the other conductors in the vicinity. Is that clear? So we can come to the inductance of a conductor, like we are assuming that we have a conductor, of course, the radius small r, and it's a circular conductor or round conductor, infinitely long. It's carrying a current of I ampere. So in that case, at lambda in, meaning the internal flux linkage, is 1 over 2 times 10 to the 1 minus 7 times the I ampere current. That's why flux linkage. But internal inductance is flux linkage per ampere of current it is carrying. So what we do when we try to find out the inductance, total inductance of a single conductor, we assume that we have a single conductor which is circular in cross section, radius is r, infinitely long, and carrying a current of I ampere. Now we have to first ensure that to do this, the reason is that we assume that the current distribution is uniform, meaning the current that the conductor is carrying is uniform, starting from the center to the last layer of the conductor, meaning across the layers of the conductor is uniform, current distribution is uniform. That's why we are trying to assume those kind of things, that is long enough and circular in cross section area, and that the other conductor. Imagine now we assuming that we have one conductor and we allowing that conductor to carry a current of I ampere. How is that possible? It's not possible. We have to have a return conductor to complete the circuit of the current. But the return conductor is also assumed that it's far away from this conductor that we are considering for calculation of inductance. So this is going to make that current distribution uniform across the entire cross section of the conductor, and it will do so. But we can find out in this conductor, we can find out the magnetic field intensity. Magnetic field intensity at any distance of x from the center of the conductor. Magnetic field intensity will be the ampere turn over the length, ampere turn per unit length, like per meter. So we can assume that can be L or L1 or whatever. So magnetic field intensity H, capital H, you know that one from physics and other electrical modules. the magnetic field ampere turn per meter. So we find out the ampere turn per meter, and then from that we find out the current, flux density beta, or B. B is flux density, so B is mu times H. If we find out the H, then we can find out flux density. B is equal to mu H. Mu is the relative permeability of the conductor material, and it comes with two values multiplied together, mu 0, mu r. Mu 0 is absolute permeability, and mu r is the relative permeability. So once we have those two, we can find out the flux linkage by taking the integral of all the flux linkages starting from the center, meaning r is equal to, small r is equal to 0 to r, and then we will be able to show that inductance is flux linkage per ampere, which is equal to 10 to the power minus 7 over 2, and its unit is Henry per meter. But if we look at this expression, what is happening here is that it's 10 to the power minus 7 over 2, 0.5 times 10 to the power minus 7, meaning it doesn't have anything that is relating to the conductor dimension or anything. In the radius of conductor, length of conductor, nothing is there, conductor. So it's independent actually of the conductor dimension. It doesn't matter how much is the radius of the conductor or how long the conductor is. So it's independent of the conductor dimension if the current distribution is uniform across the cross-sectional area of the conductor. So it's independent. Internal inductance will always be 10 to the power minus 7 over 2 Henry per meter. So that's how we calculate the internal inductance. For calculating the external inductance, we consider the same thing, that conductor of radius r carrying a current of I, and we consider the distance, any distance x from the center of the conductor to all this way, all the way to a very long distance of r, capital R, from the center of the conductor, and find out all the flux linkages here outside the conductor. And if we do so, again we follow the same thing. We find out the H, meaning magnetic field intensity, and from the magnetic field intensity we can find out the flux density. From the flux density we can find out the flux linkage, and flux linkage over the current will give us the external inductance, and that external inductance expression is just a little bit different. Internal inductance expression was 10 to the power minus 7 over 2, and this one is 2 times 10 to the power minus 7 log. This is a lim that will be used in calculator, lim, log r over r. R is the external distance, meaning the distance up to which we are considering all the external fluxes linking to this conductor under consideration having a radius of small r. So that's the external inductance expression, 2 times 10 to the power minus 7 log capital R over R. So after that we can add two of them, 2 times 10 to the power minus 7 log R by R, and the internal inductance was 10 to the power minus 7 over 2. If we add them, then we get something like this, 2 times 10 to the power minus 7 log capital R over R prime, where R prime is actually small r, meaning the radius of the conductor, times e to the power minus 1 over 4, and we know the value of E, 2.7, and then that is equal to 0.7788 r. Now these two distances r and r prime actually are the distances that are related in the calculation of, or the expression of, total inductance of a conductor. Now the distances, first one is that the distance of a conductor and all other conductors around this capital R is the distance. That capital R is the distance, if we go back, is the distance from the center of the conductor that is under consideration to a distance where all other conductors are there, and they are causing some flux to be linked with this conductor. So this R is the distance between the conductor under consideration and all other conductors. And this R prime is related to capital R, and this is a constant actually. E to the power minus 1 by 4, which is 0.7788. So this is self distance. We call it own distance. Because of its own radius, it will have its own distance. So the distance of the conductor itself, being the conductor radius or the dimension of the conductor, is related here, and the distance of all other conductors from this conductor is going to determine total inductance of the conductor, which is the very unique equation here. It will be used in this form all the way up until the end of this chapter. 2 times 10 to the power minus 7 log R by R, meaning the distance of all other conductors and the distance of the conductor itself, meaning the self distance. So we need to remember that. Now I'm coming to the next one. It's a generalized theory that came from mathematics when we want to find out the flux linkages in a group of conductors. Now we have had considered that one conductor, and we got the total inductance was 2 times 10 to the power minus 7 log R by R, and we will use that here. So we consider that we have a number of conductors in a group. Like how many, we don't know. So we are assuming that we have n number of conductors to generalize the theory. We have n number of conductors, and we label them as A, B, C, D, E, F, and all those up until n. So we have n number of conductors. So if we have n number of conductors, we can write down the flux linkages in a group of conductors like that. So that 2 times 10 to the power minus 7, that current of its own, it was inductance. In inductance equation, the current is always there. Flux linkage over current is the inductance. Flux linkage over the current is the inductance. So if we want to find out the flux linkage, it will be the 2 times 10 to the power minus 7 log R by R times the current. And you see, if we want to find out the flux linkage, it will be inductance, which is 2 times 10 to the power minus 7 times log R over R times the current. So we will use that equation here. You see, 2 times 10 to the power minus 7 log R over R, and then distance of its own, and the second conductor is coming, which is IB, the current in it, and then log the distance between them is AB, distance between them is AB, and then the next conductor is IC, so it will be IC 1 over D, A and C, and all the way the last conductor is the nth conductor, which will be carrying a current of IN, and the distance between them will be AN. So all the conductors are needed to be considered when we have a number of conductors in a group. And flux linkage lambda A as is calculated here. Flux linkage lambda A is calculated here in the flux linkage of conductor A considering its own current in the IA, plus all other currents in the conductors that are around these conductors or in the vicinity, meaning we consider the current IA of this conductor A itself in the first place, and then we go to the next conductor, meaning the B, which is carrying a current of IB. Then we go to the next conductor, which is carrying a current of IC. The next one is carrying a current of ID. The next one is currently carrying a current of IE if it is there, and then the last conductor is carrying a current of IN. So that is for conductor A is lambda A. Can do the same equation for the conductor B. So lambda B 2 times, then you are minus 7, then IB log 1 over dBB, and then B2A, B2C, B2N, and so on. When we are done with conductor B, we will go to the conductor C. So it will be lambda C. So 2 times 10 to the power minus 7 like that. Then IC log 1 over DCC. Then I will come to the next conductor DCA, DCB, DCDD, and DCN. When we are done with that, then we will go to the last conductor, which will be the nth conductor. That will give us lambda N. So we will write down the equation of lambda A, lambda B, lambda C, lambda D, lambda N, and all the way like that. So once we have that, we can find out the average of the flux linkage, and that average flux linkage will cause the inductance of the conductor in a group. Now, the reason why we are using the concept of a number of conductors in a group, meaning when we have three-phase system, we have a number of conductors in a group, meaning at least one conductor for each group. So that we call 3 conductors for each group. And then if we extend it, like yesterday I was saying, for each phase, we don't use one conductor, we use the number of subconductors. That will also come into the scenario. That's why you need to know that we have to consider all the factors that are present in the vicinity are considered in the calculation of flux linkage, and hence the inductance of the conductor. Is that clear? Okay. So we take a number of conductors in a group to generalize the theory. And that helps us when we have a three-phase system, and meaning we have a number of conductors in them, and it makes it easy for us to calculate. Now, we want to go to the single phase two-wire line. We are going to use that same concept. So inductance of a two-wire line, one is supplying current, the other one is returning current. The supplying current is plus I going out, and the other one is coming back, returning. So minus I, it should be the same current. Each of those two conductors, supply conductor and the return conductor, having a radius of r. They are located at a distance of d from each other, and we also label them as conductor A for supply conductor, conductor B is the return conductor. So for this configuration, we can find out the flux linkages for each of these two conductors, conductor A, conductor B. For conductor A, flux linkage will be 2 times 10 to the power minus 7, its own current, which is I, log 1 over its own distance, which was DAA, meaning R prime. DAA is R prime. If you don't understand this, just read the notes a little bit today, because you have the whole day. Tomorrow I will come in the morning at 8:40. I'll explain again that those expressions that you have in the notes. There are a lot of expressions in between to understand. You need to understand. Sometimes we don't like mathematics, so we don't like equations, but we need to understand them. We cannot ignore them, because the equations actually help us to understand the physical system, and from the physical system we write the equations and verify them via experimentations and so on. So they are very, very related. We cannot isolate them, we cannot ignore them. So from that previous generalization here, we can use this for this two-wire system, and we find out that the flux linkage for lambda is 2 times 10 to the minus 7 times the current that it is carrying, log E by R prime, meaning the distance between them, meaning the distance of that first conductor with respect to the other conductor around, which is capital D, and R prime is the self distance. And if we go for the second conductor lambda B, it's the same thing. It will be 2 times 10 to the power minus 7 times the current that it is carrying, which is I, and then log D by R. And D is the distance of this conductor with respect to the other conductor A, and R prime is own of self distance. So when we have that, we can calculate the total inductance of the conductor. Right, and then we can go from there, find out the inductance to be the same for each of these conductors. Lambda A is the flux linkage for conductor A, lambda B is the flux linkage for conductor B, and if we divide by the current, meaning lambda A over I is 2 times 10 to the minus 7 log D by R. Lambda B over I is also the same, so the flux linkage is the same. So lambda A over I and lambda B over I is the inductance of each conductor, and they are same because they are carrying the same current, because they having the same radius R, and they are separated from each other by a distance of D. So that is causing the inductance of each of these conductors A and B to be the same. And if we want to find out the loop inductance, meaning the total loop starting from the supply conductor A to the return conductor B, the loop will be completed. And if the loop is completed, we have to consider the inductance of two conductors A and B. So if we consider the inductance of two conductors A and B, it will be the sum of these two inductances, meaning inductance of conductor A, which is 2 times 10 to the power minus 7 log D by R prime, plus 2 times 10 to the power minus 7 log D by R prime. So it will be the double of inductance of any conductor of A and B. Is that clear? Not clear. Okay. What you said, no, said? Does it mean that it's not clear? Yeah, it's fine. Okay, now we're coming to inductance of symmetrical three-phase. From single phase, we're going to three-phase line or three-phase system. Meaning we have three phases A, B, and C. We label those three conductors for three phases, and A and B and C, and they are configured as symmetrical in three-phase line. Meaning we put the conductors on the vertices of that equilateral triangle, meaning they are separated by the distance D. If we assume the distance between any two of them is the capital D. So in that case, what will happen? The inductance of each of them will be 2 times 10 to the power minus 7 log D by R prime. It will be the same. The reason is that we have to consider the first one. What is its inductance? 2 times 10 to the power minus 7 log D by R prime. Then we take the second conductor between A and B and between A and C. We consider all the distances, meaning the current flowing through it is IA, the current flowing through is IB, current flowing through it is IC, right? And the distances of its own, if the radius is smaller, the self distance will be R prime, which is 0.7788 times smaller, and the distance between them is always capital D. And if we write those equations following that one, then we'll find out that it will always be equal to 2 times 10 to the power minus 7 times log D by R prime for each and every conductor of a three-phase equilateral triangle. If we have this kind of arrangement, and we call it symmetrical spacing, meaning the conductors are symmetrically spaced, meaning the distances between them is the same, A and B, B and C and A. All the time it will be the same. But to make this type of thing happening in real life or on a transmission line is going to require some special arrangement so that the distances between the phase conductors B and C are always same, and we need more attention to the design. This is the best one, but it needs special attention to the design to maintain the distance, and it costs some money as well. That's why in most of the cases we end up having unsymmetrical spacing or unsymmetrical arrangement, meaning the distances between the three conductors of three phases are not the same. So if that is not the same, then how it looks like? It might look like that A, B, C, three conductors are there, and the distances between them are no longer the same, meaning it's not capital D anymore. The distances are different. Between A and B, the distance is D12, and for the conductors between B and C, the distance is D23, and for the conductors C and D, the distance is D31. So the distances are different, so that makes it unsymmetrical. Now, when it becomes unsymmetrical, three conductors will have three different inductances. It will depend on the same thing. 2 times 10 to the 1 minus 7 log d by r prime, and that d will be coming from the three distances d12, d23, and d31. And sometimes we take the mean of these three distances, and the mean is what? We multiply all these quantities that are there in the expression or under consideration, and we take corresponding root. Mean is always calculated, geometric mean is always calculated like that. If you have two parameters like d12 and 21, so meaning the distance, I'm trying to find out the distance between these two conductors. So what I can do, I can measure the distance from here to there, and I also can measure the distance from here to there. And now I have two distances. I want to take the mean, meaning I multiply those two distances that I have measured and then take the corresponding root, meaning I have two distances, I'll take square root. If I have three distances like 1, 2, 3, 3, 1, I'll take cube root. If I have four distances, I'll take 1/4. The power will be raised to 1/4. If I have 8 distances, the power will be raised to 1/8. In this case, we use the theory of geometric mean, and we assume that it will give us an average value or mean value of the inductances of these three-phase conductors, which are not the same because of the unequal distances between them. But what we try to in real life, we don't like unequal inductances for each phase, because what will happen with unequal inductance in each phase? It will cause unequal voltage drop for each phase, which we don't like. Unequal voltage drop we don't like. Also, that will cause some unbalanced voltage at the receiving end. Unequal voltage drop because of unequal inductance will cause some voltage drop which are different. That will lead to the unbalanced voltages at the receiving end, and because of the unbalanced voltage at the receiving end, the appliances or the equipment that are connected to that unbalanced voltage system will not operate satisfactorily or as desired. So we need to deal with that in real life. But that is the easiest way to put the transmission line conductors, as if you go and put there, it will become unsymmetrical by nature. Also, there is another thing that when we have unequal spacing between the conductors giving us unsymmetrical three-phase line, there will be some interference with the neighboring communication lines. In olden days, power line carrying communication, PLCC, was there, power line carrying communication, because not only we were sending power from one into the other, we needed to send some communication to the receiver from the sender that we sending power. This is the voltage, this is the current, this is the frequency, and all those things. So power line carrying communication were also run along the length of the power line, and that was being interfered by this unsymmetrical nature of three-phase system, which has unsymmetrical arrangement in terms of the spacing between the conductors. So we want to avoid that, and then what we do, we call it transposition. What we do something called transposition, and the transposition meaning is the of these three conductors in cycles, meaning in the next step, next cycle, something like that. So if we assume that in the first place, these three conductors A, B, C are having these three positions, position 1, 2, and 3, top, middle, and bottom. So conductor A is at the top, conductor B is in the middle, conductor C is at the bottom. So in the next cycle, what we will do, we'll change their position. So conductor A is coming to the middle, conductor B is going to the bottom, conductor C is going to the top. And in the next cycle, we will go and change once again their position. So now C is going to the middle, A is going to the bottom, B is going to the top. And once we have these three cycles, first cycle, second cycle, and third cycle, meaning we have three different positions for each of these three conductors, meaning we have transposed them, we have changed their position in such a way all of them have assumed same positions at some point. So A has top, middle, bottom. B has top, middle, bottom. C has top, middle, and bottom. Now it seems like they are all the same because we have changed their position, and this method is called transposition. This method is called transposition. Once we do that, we really get a true average value or true mean value of inductance for each of those three conductors, and they really become equal, and they don't cause any more interference with the transmission lines that are nearby, and also they cannot cause unequal voltage drop due to unequal inductance of them. They cannot cause unbalanced voltage at the receiving end. So to avoid interference in the communication lines, to avoid unequal inductance, to avoid unequal voltage drop, and hence unbalanced voltage at the receiving end, we do the transposition by changing the position of each of the conductors in cycles or steps. But when we do this in physical system, meaning physical transmission line, it becomes expensive. The reason is that we have to have special tower. Now imagining the A conductor was at the top, meaning the conductor A was at the top. Now I have to bring that conductor down to the middle one. So for that one, we need special type of towers. In the next one, we need to bring down the conductor A to the bottom. We need special. So we call those towers transposition towers, like we heard yesterday. We have suspension tower, a conductor suspended from the insulator, connected to the transmission line tower. Then we have tension tower, meaning the conductors are subjected to tension when the power line is changing its direction, or the line is ending, or the line is crossing a railway bridge, or a railway track, or a bridge, or a river, or national highways. So tension tower is there. For this transposition, we need special type of towers called transposition towers, and it's expensive. We have to construct or build those special type of towers, and that causes some expenditure. And when we do this in real life, we don't take these distances between them to be very long. We want to finish this thing very quickly. Within a short distance, within hundreds of meters, we are done transposition. Then we carry them all the way because now they have balanced. Is that clear? Okay, if you have any question, you can ask.